Okay, so next we are going to see a simply supported beam. SSB is nothing but simply supported beam. Simply supported beam subjected to an eccentric load or eccentric point load, we can say, which is nothing but other than at the middle, the point load may act anywhere along the length of the beam. It can act anywhere except at the middle. We call it as an eccentric point load. Okay, so now here the load is acting at a distance A, small letter A from the left hand support A, and distance B from the right hand support B. Okay, here in this case A is less than B. Okay, A is less than B. Now similarly we have to find out the support reactions, unknown support reactions RA, RB. So let me take a moment with respect to A. Okay, so W into A gives clockwise moment and RB into L gives anti-clockwise, so negative. So RB is equal to WA by L. Similarly, sigma Fy is equal to 0, RA is acting upward, RB is acting upward, RA plus RB, and W is acting downward, so minus W. Substitute RB, you will get RA. RA is equal to WB by L. Okay, so now let us draw the shear force diagram. Okay, since we have obtained the values, unknown support reaction values RA and RB, and this is the baseline or reference line on which the shear force values are 0. On the top we are going to plot the positive values, and at the bottom we are going to plot the negative shear force values. Okay, so let us consider a section X at a distance X from the left hand support. Okay, SF at XX, SF is having unit Newton and RA is also having Newton. Okay, so to the left side of the section XX, only force acting is RA, acting upward. From the left hand side, upward is positive. So RA is nothing but WB by L. Okay, WB by L. So it's increment acting upward. So this is nothing but WB by L. Between A and C, no load is acting. So the shear force remains constant. So once we reach the point C, okay, W is acting downward. So WB by L minus W. So the shear force at C is minus WA by L minus WA by L. So this is the positive value. This is the negative value. So this is the WA by L and this is the WB by L. If you add, you will get W. Okay. Then between C and B, there is no load. So shear force remains constant. And this is nothing but equal to the value RB. RB is nothing but WA by L, which is nothing but from right hand side, if you proceed upward is upward shear force is negative. So minus WA by L. Okay, you can complete it. So WA by L and this is WB by L. This is positive and this is negative shear force. Okay, and this is a shear force diagram. And when you go for the bending moment, similarly write down the expression RA into X, RA into X. At A, X is 0, right? At A, X is 0. So bending moment at A is 0. Okay, mathematically you can prove it. So here it is 0. Then at C, X is equal to A. Substitute X is equal to A here. Already RA is nothing but WB by L. So in place of X, substitute A. You will get bending moment at C is nothing but WAB by WAB by what is that? I think okay. So at C x is equal to A. Okay. So in this expression you just substitute here. You will get at C x is equal to A. So bending moment at C will be WAB by L. Okay. Earlier it was by it's a typing mistake. Earlier I was typed as WAB by 4. So it should be WAB by L. So this is the maximum bending moment for a simply supported beam subjected to an eccentric point load. So at A, bending moment is 0. At C, bending moment is WAB by L. The nature of the bending moment diagram is a triangle in nature for a point load. Okay. So we know that the bending moment is 0 at the simply supported end here. So we can just connect it by a straight line from the maximum to this point B, and this is a positive bending moment. Okay, so this is the bending moment diagram and this is the shear force diagram for a simply supported beam subjected to an eccentric point load. So next, simply supported beam subjected to an UDL, uniformly distributed load over the whole span. So let me consider a simply supported beam, okay, of length L, uh, subject to UDL W, W per unit length. So Newton per meter is the unit for UDL, and for UVL whatever it is. Okay, UDL UVL is having same unit. Load per unit length, that is Newton per meter. This thing we should keep in mind, very important. Now let us find out the support reactions RA and RB. So taking the moment about A, okay, so W into L, okay, W into L, this is the Newton per meter, L is in meter, so Newton per meter into meter becomes a Newton, which is a force. When this UDL is multiplied by its run length or spread length, it becomes a point load, and that point load will act at a distance exactly half of the run length, that is Newton per meter into meter becomes a force Newton, where it will act exactly at a distance of L by 2, L by 2. So that force where it is acting into its distance, perpendicular distance, L by 2. So W is Newton per meter into meter. This becomes a Newton into L by 2. Okay. This W into L will act exactly at a distance of L by 2. That you need to remember. Okay. So W into L by 2. And this RB gives anti-clockwise. So RB into L. Okay. So RB is equal to WL by 2 is the support reaction. And sigma Fy is equal to 0. RA plus RB. And W into L is the total load acting, which is acting downward. So minus. So RA is equal to WL by 2. Now how to draw or how to plot the shear force diagram. Okay, at A, RA is acting upward. Okay, so let us consider a section XX at a distance x from the left hand support A, SF at XX. So to the left side of the section, we have to consider the forces acting. RA is acting upward. Shear force is having unit Newton. RA is also having unit Newton, whereas W is having the unit. UDL is having the unit Newton per meter. So it must be multiplied by the run length to get a unit Newton. So W into X. X is the run length under consideration. This is a section we have taken. So this is the run length. Newton per meter into meter, it becomes a Newton. This UDL is acting downwards from negative. We are proceeding from left hand side. So upward is positive, downside is negative. So at A, X is 0. So substitute here X is equal to 0, which gives shear force at A is nothing but RA, which is equal to WL by 2. So RA is shown by a vertical line, increasing line, moving upward. Okay, because it is a positive. Okay. Then at C, X is equal to L by 2, substitute here. So this is WL by 2 minus here X is equal to L by WL by 2, shear force is 0. Okay, so the nature of the shear force diagram for UDL is a triangle in nature. So here it is 0. Okay, then since we don't have any load between A and B, and there is no any discontinuity between the loads, okay, so this expression SFX, the SFXX is valid throughout the length, that is between the two supports. So X is equal to, X varies from 0 to L. So at B, X is equal to L. The shear force at B is nothing but minus WL by 2. Okay, so minus WL by 2, which should be shown below the line. Okay, so from the right hand side, upward force is shown by a negative value, right? So this is the negative value, and you just connect it from this 0 to this negative value. So this is the shear force at B minus WL by 2, or RB is equal to WL by 2. From right hand side, this negative. Complete the diagram. So this is the positive shear force, and this is the negative shear force. So here the shear force is 0. Now write down the bending moment expression to plot the bending moment diagram. So BM at XX to the left side of the section. Force into perpendicular distance RA into X from the left hand side, clockwise positive and clockwise negative. RA into X clockwise positive. And this W UDL multiplied by run length W into X with respect to this W into X gives anti-clockwise. So minus W into X becomes a Newton, where it is acting at a distance of X by 2, X by 2. So into X by 2 is the moment arm or perpendicular distance. So Newton into meter, Newton meter, which is the unit for moment. At A, X is 0, substitute here, so bending moment at A is 0. Then at C, x is equal to L by 2, bending moment at C is WL square by 8, which is the maximum bending moment for a simply supported beam subjected to UDL over the whole span. Sometimes it's called as over the entire span, something like that, or entire length. So here it is 0. So here it is 0. So this is the maximum value here, WL square by 8. Okay. So the nature of the bending moment diagram is a parabola for UDL. So it is connected 0 here, going like this, reaching maximum WL square, then it is dropping at B, it is 0. So it's a parabola. So as I told you the important points, at a point where the shear force is 0, bending moment will be maximum. Okay. And the bending moment is 0 where the shear force is maximum. That we need to keep in mind. Okay. Thank you.